Let's talk about the conservation of momentum lab. Before we dive into the lab, I will cover and review a little bit of a theory behind the conservation of momentum. So if you remember, momentum was the product of mass times velocity. Momentum is a vector, so I use an arrow, vector notation, because the velocity is a vector. All right? And if you remember, based on Newton's second law, F equals ma, we could rewrite this F equals ma using the definition of acceleration, which is the change of velocity over change of time. So in other words, this acceleration here is change of velocity over change of time. All right? What I can do is to rewrite this like so. M, instead of delta V, I'll have V final minus V initial divided by delta T. And I can distribute this mass and multiply it by V final and V initial. So I have mV final minus mV initial divided by delta T. So force is this mass times V final is momentum final. This mass times V initial is momentum initial. Therefore, I have P final minus P initial divided by delta T, which I can write it as delta P divided by delta T. Okay? So all I'm doing here is I defined, one more time, I reviewed what the definition for momentum is, mass times velocity, and I went to Newton's second law. Okay? Newton's second law, F equals ma, but I write a, or acceleration, as the way that we defined it, delta V divided by delta T. All right? And I play with this delta V divided by delta T, and then I ended up getting to a form like so. F, which is the force, is delta P, change of momentum divided by delta T. Now, what the usage for this formula is that a lot of times when we're dealing with collisions between two objects, all right, we wanted to see if the momentum is conserved. And so we rewrite this equation for a particular reason. If force, in this case the external force, is 0, then using this equation in the box, I can write that delta P is 0. This means P final should be equal to P initial. Or in other words, the momentum is conserved. Okay? The momentum is conserved. It doesn't change if external force is 0. So if you have a system, an isolated system with no external force, the total momentum of a system should remain constant. There might be one particle or a few particles that the momentum changes for those if you have a system of particles, but for the other particles, it will change in such a way that the momentum will remain constant, okay, if there is no external force. Now, let's talk about one of the applications of conservation of momentum, and that is whenever that we have two objects colliding. We have two different types of collisions. The first type of collision is called elastic collisions. For elastic collisions, you have two objects, M1 moving with some sort of velocity, let's call it V1, and let's say that you have M2, object 2 with mass M2 moving with some sort of velocity, initial velocity V2. They collide with each other, okay? And M1 will have V1 final. And let's say that M2 is going in the opposite direction, V2 final. All right, so I'm going to label them final and initial. So this is final. All right, and these are initial. All right, so we have two objects, M1 and M2. They collide. The initial velocity of V1 and V2. After collision, they have some sort of final velocity, and the direction for those two final velocities doesn't matter. All right. Again, we have the same objects, M1 and M2, but we have a different type of velocity now for them, V1 and V2 final. The important part is that these two velocities, these two objects are not combined. They are not deformed. They collide and they bounce back. They bounce off of each other. They don't combine. They don't smash together. They don't make a sound. They don't deform. If that's the case, we call those type of collisions elastic collisions. For elastic collisions, not only momentum is conserved, meaning M1 V1 plus M2 V2 initially equals to M1 V1 plus M2 V2 final. Not only that, but also kinetic energy is conserved. Okay, so half M1 V1 squared plus half M2 V2 squared initially should be equal to half M1 V1 squared plus half M2 V2 squared finally. So it's important to note that if two objects bounces off, they don't deform. They remain the same objects as they were before collision. Then we're dealing with elastic collisions. For elastic collisions, we have conservation of momentum and conservation of kinetic energy. There is another type of collision. The second type of collision is inelastic collisions. For inelastic collisions, you have the same setup as before. All right, you have the same setup. You have one object with initial velocity v1i, another object with the other velocity v2i. I means initial. They collide, but this time after collision, they're deformed, they stick together, and we only have one deformed object with mass m1 plus m2. They kind of stick together like two cars that are having a head-on collision and one car is stuck to another car. And this time we have some sort of velocity. I just wanted to call it final. They both have that same velocity. They stick together after the collision. There is a sound, there's a deform, there's some sort of energy released after the collision. But the most important part is that those two objects are now one object. Okay? If that's the case, we're dealing with inelastic collisions. For inelastic collisions, momentum is conserved. P initial should be equal to P final. However, that's very important, kinetic energy is not conserved because some of the energy is released and formed. It changed to thermal energy, to heat. Some changed to sound. So the kinetic energy is not conserved, but momentum is always conserved, meaning momentum initially, which is m1 v1 plus m2 v2 initially, before they collide, should be equal to momentum finally. Momentum, we have one object now because they stick together with mass m1 plus m2 with the velocity v final. Okay? So here's a little bit of a background before we dive into the experiment, and we'll show you what the setup would look like, and we'll provide you with the data. Here are some of the things we need. We need 2 gliders, 2 Volcros, 2 rubber bands, and 2 flags. We need the air track, and we also need 2 photo gates that are connected to our computers. What photo gates does is that whenever that a glider is passing through it with the flag on, the flag will momentarily block the laser in the photo gate, which in return the photo gate connected to our computer will show us the velocity of a passing glider. The first part of the experiment, we are going to do the inelastic collision. In inelastic collision, the 2 objects, in this case 2 gliders, will stick together. We use Velcro so that when the 2 gliders are hitting each other, they stick together. The first glider will pass through the first photo gate, and we'll measure the velocity of that glider using the first photo gate. Once they both connected using the Velcro, they pass through the second photo gate, and we'll measure the velocity of them passing through the second photo gate. First photo gate, sticking together, passing through the second photo gate, and we'll measure the velocity. Each photo gate will give us the velocity of a passing glider. Remember, this is inelastic collision, so momentum is conserved, but kinetic energy is not conserved. The next part of the experiment, we're going to do the elastic collision. So we're going to use the rubber bands instead of the Velcro. We're going to have 2 flags, and the gliders will bounce off each other, as you can see. First glider bouncing off the second glider. We measure the velocity of the first glider using the first photo gate. It bounced off. The second glider will pass through the second photo gate, and we'll measure the velocity of that using the second photo gate. Remember, for the elastic collision, both the kinetic energy and the momentum is conserved. So Pi equals Pf and Ki equals Kf.